The Great Attractor is erasing the universe. The sky isn't still. Our entire galaxy is sliding 600 kilometers a second towards something we can't see. Instruments show it. The cosmic background glows a hair warmer in the direction we're falling, a fingerprint of motion baked into ancient light. Astronomers call the destination the Great Attractor, and the route to it runs through a blind strip of sky our own Milky Way blocks. Here's the catch. Even if gravity wins locally, a larger force is stretching the map itself. Before we decide who's stronger, pull or push, we need to rewind to the first clue that said our neighborhood was drifting. Roadmap as escalating revelations. We'll track this story like a current you can feel long before you see the river. First, the symptom. Peculiar velocities. Galaxies weren't just riding the expansion. They showed a drift, a direction, a speed that didn't fit the Hubble flow. The evidence sharpened with a simple, devastating signature. The dipole pattern in the cosmic microwave background, telling us we're in motion relative to the oldest light. Then we hunt the source. The early suspects point toward the Virgo cluster, then past it into a region we can't easily map because the Milky Way's disk smothers the view. Astronomers nicknamed that swath the zone of avoidance, and for years it lived up to the name. We'll watch as infrared, radio, and X-ray surveys punch through the dust to reveal something stranger than a single monster. A basin, a gravitational valley that redefines our home address as Laniakea, the immense heaven of 100,000 galaxies flowing toward a low point. But the map keeps expanding. Beyond the Great Attractor sits the heavyweight Shapley concentration, and there's a second character we didn't expect. A vast, underdense region, the Dipole Repeller, acting like a push from behind while mass ahead pulls. The flow is a tug of war with two ends. Only then do we step back to ask the big question. What happens to a river of galaxies in a universe driven by dark energy? We'll weigh endings. Heat death, big rip, vacuum decay, and ask what the data favors now. Finally, we return home to the Milky Way's future. What we keep, what we lose, and what erased really means. The first weird clue. Peculiar velocities. To understand why astronomers smelled a current at all, you have to separate two kinds of motion. One is the Hubble flow, the smooth expansion that carries galaxies apart like dots on a stretching sheet. The other is everything on top of that. Local pushes and pulls from gravity that make dots drift relative to the sheet. Those are peculiar velocities, and in the late 20th century, they started to look coordinated. The first hints weren't explosions, but gentle tilts in the data. Surveys of galaxy distances and redshifts showed that, after subtracting the expected Hubble expansion, there was a residual motion in a specific direction. It wasn't chaos, it was a bulk flow. Meanwhile, a cleaner, global test lit up. The cosmic microwave background, the afterglow of the hot early universe, should be uniform in all directions once you account for small primordial ripples. Instead, it's ever so slightly brighter in one half of the sky and dimmer in the opposite half, a hot-cold dipole. That pattern is exactly what you'd expect if we were moving through the microwave sea, like a swimmer feeling colder water on their back and warmer on their face. Measure the amplitude, and you can infer our speed, roughly 600 kilometers per second, toward the constellations Centaurus and Hydra. Stakes, in human terms, were immediate for the field. If the numbers were right, then something on scales bigger than the local cluster was tugging on not just the Milky Way, but our entire local group. When teams tried to pin the culprit, they looked first to Virgo, the nearest massive cluster, because in the nearby universe, Virgo is the usual suspect. But Virgo's mass wasn't enough to explain the full velocity. The drift seemed to point past it, into sky hidden by our own galaxy's plane, thick with stars and dust that scatter visible light into a fog. That obstructed region got the name you'd give a place you can't map, the zone of avoidance. Action moved to wavelengths that don't care as much about dust. Infrared surveys started to pick out galaxies peeking through. High, radio observations, listening for the 21-centimeter whisper of neutral hydrogen, sketched filaments and clusters in silhouette behind the Milky Way's glare. X-ray maps lit up hot gas in hidden clusters. Piece by piece, a concentration emerged in the direction of Norma and Centaurus. Not a single monster, but a crowded intersection of clusters. The press called it the Great Attractor. Scientists were more cautious. It was a name pinned to an effect we inferred from motion more than a luminous beacon we could see. Impact came in the way astronomers thought about maps. Up to then, we told the story of structure like a stack of still photos. Galaxies, clusters, superclusters. Peculiar velocities forced a flip. Instead of a static atlas, you need a flow map. Teams like Cosmic Flow started measuring distances carefully, correcting redshifts for the expansion, and drawing streamlines, arrows showing where galaxies move after you subtract the Hubble flow. Those arrows didn't radiate from a single point. They converged into a broad valley, like water lines bending toward a basin. Our neighborhood wasn't falling onto a lump. It was sliding downhill across a gravitational landscape. Meanwhile, there was an irony. The same data that said, go this way, resisted the old narrative of a lone attractor. As catalogs deepened, another pull showed up farther out. Past the Great Attractor lay the Shapley concentration, a sprawling complex of clusters that could account for a chunk of our motion. And models suggested something else might be in play behind us. A large, underdense region, less mass than average, effectively letting structure flow away from it. That idea would be fleshed out later as the Dipole Repeller, but its fingerprint was already hiding in the flows. You see faster motion where there's a downhill ahead and less resistance behind. A micro-story captures the shift. In a control room, a researcher overplots peculiar velocity vectors on a new infrared catalog. The arrows bend across the zone of avoidance toward a patch no optical chart shows. The student next to them frowns and says, "So it's not a thing, it's a place." The senior scientist nods. "It's a place in the potential." That sentence reframed the hunt. We weren't chasing a single hidden beast. We were mapping the contours of a gravitational field carved by dark matter, galaxies, and gas. The consequences ripple. If flows define basins, you can define superclusters by watersheds, not arbitrary boxes. That's how Laniakea would be drawn, a region where flow lines descend toward a low point near Norma. And once you see the universe in motion, you can ask smarter questions. What fraction of our 600 kilometers per second comes from mass here? Mass farther out, or from a lack of mass behind? How does that add up against the backdrop of a universe whose expansion is accelerating because of dark energy? Peculiar velocities were the first clue that we live in a river. The next act is following it through the fog. The Great Attractor emerges. To follow the river through the fog, astronomers had to change how they looked. Visible light was useless across the Milky Way's midplane. Stars and dust turned the target into a smear, so they switched to wavelengths that slipped through grit. In the 199s and 200s, all-sky infrared maps from missions like IROS and 2MASS began pulling faint reddened galaxies out of the glare. Radio telescopes tuned to the 21-centimeter line started hearing neutral hydrogen where eyes saw nothing. X-ray observatories picked up the hot intracluster gas that marks where gravity has pulled matter tight. Layer those views, and the blind strip wasn't empty at all. It was crowded. What took shape wasn't a single mountain, but a knot of ranges. In the direction of Norma and Centaurus, beyond the nearby Virgo cluster, infrared and radio catalogs revealed the Norma cluster, Abel 3627, a hefty anchor buried deep in the zone of avoidance. Around it, the Hydra Centaurus region lit up with additional clusters and filaments. X-ray maps showed elongated, glowing reservoirs, gas at tens of millions of degrees, confirming the presence of serious mass. This was the heart of the effect Lyndon Bell's Seven Samurai had inferred from motions, a gravitational convergence zone. The nickname Great Attractor stuck because it felt right, even as the details got subtler. The subtlety matters. Mass doesn't gather as one smooth lump. It webs. Dark matter, which doesn't shine, sets the scaffold. Galaxies and gas trace it imperfectly. What the instruments were picking up were the bright beads on that web and the hot fog between them. When teams reconstructed the gravitational potential from peculiar velocities, how hard the downhill pulls across space, they found the valley floor was broad and flat in places, not a spike. That's why our flow lines don't aim at a single point, but curve into a basin centered near Norma. The Great Attractor is shorthand for an overdense region whose pull is distributed, not a black hole gulping everything down. One day crystallized this new picture for a lot of people. The Parkes Radio Telescope in Australia had just upgraded its receiver, and the HI Zone of Avoidance survey was deep into its sweep. On a Monday morning, the team plotted their latest detections. Hundreds of hydrogen-rich galaxies hidden behind the Milky Way's band. The dots thickened across an area previous catalogs left blank. A postdoc traced a finger from Centaurus toward Norma and said, almost to themselves, "There it is. Not a single it, but a route. Filaments feeding a crowded hub." That map went up on a wall and stayed there. It told the story in one glance. Mass where there hadn't seemed to be any, exactly where the flow pointed. Stakes follow for how we defined our address. If flows converge into basins, you can draw boundaries by watershed. In 2014, using thousands of galaxy distances and the cosmic flows reconstructions, researchers did exactly that. They traced streamlines and carved a supercluster by where the lines ended up. They called it Laniakea, immense heaven. In that map, the Great Attractor is the low place, the gravitational sink toward which 100,000 galaxies drain. Suddenly, our local group wasn't a dot in a box. It was a kayak in a river system, its path determined by contours you can't see but can feel. But even as the Great Attractor came into focus, another truth pressed in. It doesn't act alone. Peculiar velocity models that fit the data best needed mass beyond the Norma Centaurus complex. Look past the basin and you hit the Shapley concentration, a titanic assembly of clusters deeper into the same general direction. Its gravity tugs on us too. Meanwhile, the flows hinted that the space behind us is different, underdense enough that matter falls away, enhancing our net motion. Later work dubbed that emptiness the Dipole Repeller. Together, they form the push-pull that shapes our peculiar speed. A dense valley ahead, a high, sparse plateau behind. There's a practical payoff to this messy picture. When you correct the galaxy's redshift for Hubble expansion to measure distance, you need to account for local flows. Misjudge the Great Attractor's reach, and you skew the Hubble constant. Overestimate Shapley's grip, and you misplace clusters. The better we map the zone of avoidance, the cleaner our cosmology gets. New surveys are helping. Deeper infrared counts, larger HI catalogs, and wide-field X-ray missions are filling in the hidden half of the sky. Each new filament or cluster pinned down reduces the guesswork in the flow field and sharpens the basin's outline. There's also a human beat to the chase. A graduate student, eyes sore from flipping between wavelengths, drags an X-ray contour over a radio map. A cluster's hot atmosphere hugs a swath of hydrogen-rich galaxies like a fog bank. They grin. Not because they found a monster, but because two very different messengers, photons from hot gas and a whisper from neutral atoms, agree about the same invisible slope. Meanwhile, across the hall, someone runs a velocity reconstruction that for the first time stabilizes without forcing a single-point mass in the zone of avoidance. The model breathes. The basin holds. So the Great Attractor emerges not as an object, but as terrain. A gravitational lowland carved by dark matter and stocked with clusters like Norma and Centaurus, masked by our own galaxy's glare and entangled with heavier pulls farther out. We're sliding into that low, yes, but the river doesn't end there, and the map stretches far beyond. The next question is obvious. If our basin is only part of the story, what does the whole watershed look like when you include the tallest nearby range, Shapley, and the empty highlands behind? Naming the supercontinent of galaxies, Laniakea. If you want to know where you live, you don't start with a dot, you start with the currents around it. That's what the Cosmic Flows teams did. They took thousands of galaxies with carefully measured distances and redshifts, subtracted the universal expansion, and watched where the leftovers, peculiar velocities, actually go. Then they did something deceptively simple. They followed the arrows. Picture a relief map where elevation is gravity's potential. High ground is sparse, low ground is dense, and rivers are galaxy motions. When they traced those streams, the lines didn't end at the bright beads we already knew. Virgo, Centaurus, Hydra. They converged into a broad gravitational low centered near the Norma cluster. Flow lines from hundreds of millions of light years away sloped down toward the same basin. Boundaries emerged the way watersheds do. If a galaxy's motion descended toward Norma's lowland, it belonged to our basin. If it spilled the other way toward Perseus, Pisces, or Coma, it didn't. That's when the name arrived. Laniakea, immense heaven in Hawaiian, wasn't just a label. It was a statement about how to draw the map. Instead of carving the sky into boxes by brightness or guesswork, they used dynamics. The numbers are staggering. Roughly 500 million light years across, about 100,000 large galaxies. and on the order of 100 quadrillion suns of mass stitched through filaments and clusters. Our local group sits out on the basin's shoulder, a tributary feeding inward. The Great Attractor is the low place, not the sovereign, an emergent feature in an uneven landscape. A micro-story from that moment says more than a plot. In a conference room, the flow map came up on the screen, a sea of white arrows bending like a time-lapse of winter winds. Someone dimmed the lights. A senior astronomer traced the ridgeline, where flows split and circled the low. "This," they said, "is home." The room was quiet because home just got bigger than anyone was used to saying out loud. Emotionally, it lands like seeing your neighborhood from above for the first time. We've spent a century naming ever larger structures, cluster, supercluster, but this felt different because it moved. You're not in a pile, you're in a river system. The stakes shift with that view. Boundaries by watershed mean that the Milky Way shares its address with galaxies you'll never see again after a few tens of billions of years, because cosmic acceleration will stretch the larger map. Within Laniakea, gravity still guides the flows. Beyond, dark energy draws the coastlines apart. Technically, the watershed approach solved problems that had nagged for years. Why did the old, local supercluster box miss obvious connections? Because light alone can lie to you. Dust hides, X-rays bias toward hot clusters, infrared misses quiescent ellipticals. Velocity fields don't care what shines, they care what weighs. By reconstructing the three-dimensional pattern of motions and inverting it into a gravitational potential, researchers could identify the true basins. The Norma Centaurus Hydra region defines Laniakea's core, not because it's prettiest, but because the arrows say so. There's humility built into this. Laniakea is not gravitationally bound as a whole. On the longest scales, dark energies push winds. The basin stretches, and only the deepest wells, clusters like Virgo or Norma, stay coherent. But for now, the flows are real. Our kayak points downstream. If you run the movie forward, our local group merges with Andromeda in a few billion years, drifts deeper into the basin's influence, and yet, in the far future, watches most of Laniakea slip past the horizon. The name holds both truths, immense heaven and finite sight. Meanwhile, this mapping opened the door to the next twist. When the team extended the flow reconstructions beyond the basin, the arrows didn't stop at the Great Attractor's floor. Some bent farther, toward the Shapley concentration, a massively overdense district like a range beyond the valley. Others seemed freer because, behind us, the terrain sits higher and emptier than average, letting matter slide away. In that geometry, pull and push aren't rivals. They're two sides of the same slope. So we have a gravitational supercontinent with rivers you can chart and a name you can say. But the ground under our feet is moving, and there's a heavier range waiting downriver. The map just got bigger again. Shapley, the heavyweight beyond. While the basin at Norma explains why our local arrows bend, the deeper pull sits farther downriver. Astronomers had hints decades ago. Beyond Hydra, Centaurus. Redshift surveys sketched an extraordinary overabundance of clusters gathered across a few 100 million light years. They called it the Shapley concentration, after Harlow Shapley, who mapped the sky's large-scale structure before we had computers to carry the load. Think of it as a mountain range past the valley floor, a stacked complex of clusters whose combined gravity can reach across Laniakea and tug on our entire basin. Here's where numbers stop being intuitive. Shapley isn't a single cluster. It's a thicket of them, with masses that together rival or exceed anything comparable within a billion light years. Its densest knots glow in X-rays, from gas-heated to tens of millions of degrees. Optical surveys count galaxy after galaxy in tight packs. Peculiar velocity reconstructions that include those depths change the story. The Great Attractor becomes a way station, not the final destination. The flow lines that dive through Norma keep leaning, past the basin's low, onward toward Shapley's greater weight. A stakes moment arrived when teams fit our local group's 600 kilometers per second motion with multiple contributors. Virgo provides a slice. The Norma Centaurus hub adds more. But to match the amplitude and direction of the CMB dipole and the galaxy flow field, you need a long-reach term. Shapley's mass supplies it. That's the pull-through story. The Great Attractor isn't a sink that ends the journey. It redirects you, like a gentle saddle, aiming you toward the dominant mass beyond. If you could paint the gravitational potential from our vantage, you'd see a subtle downhill toward Norma that tips more steeply toward Shapley's ridge. Action moved from catalogs to reconstructions. Cosmic flow-style inversions that extend their volume farther into the southern sky show the streamlined geometry change character as you pass Hydra Centaurus. Lines that fan inward tighten and align toward Shapley's core. When you separate contributions in the model, mask Shapley, and watch the residuals, the predicted local motion slumps. Put Shapley back and the vectors recover. Different datasets tell the same story. SNEEA, distances, surface brightness fluctuations, Tully, Fisher measures. The specific weights vary, but the pattern doesn't. Shapley matters. Meanwhile, the zone of avoidance plays a quieter role here. We don't see Shapley through the Milky Way's midplane. We see it around the edges where dust thins. That's fortunate. Clusters like Able 3558, 3562, 3556 light up cleanly enough to anchor mass estimates. X-ray temperatures, galaxy velocity dispersions, weak lensing signals, each one a ruler on the same scaffolding. Stack those rulers, and you get a mass that justifies a long-arm tug. The uncertainties live in the outskirts, where filaments feed the core. But even conservative bounds leave Shapley as the southern sky's heavyweight. A micro-story captures how the picture clicked. In a small office, a researcher ran 2 reconstructions back-to-back. First, they truncated the data at Laniakea's edge. The flow field curved into the Norma basin and settled. Then they added a deeper shell with Shapley's clusters and resolved. The basin's floor tilted. Arrows that had relaxed reoriented like iron filings under a magnet nudged to a new angle. They printed both frames and taped them up. This is why the dipole points where it does, they wrote under the second. It wasn't poetry, it was relief. Debate followed, the good kind. How much of our motion is locally sourced versus long range? Does the Great Attractor contribute half and Shapley a third, or vice versa? Different teams landed on different splits depending on distance ladders and masks, but the consensus held. You need both. A dense valley ahead and a denser range beyond. Fold in the emptiness behind, the dipole repeller's underdensity, and you get the full geometry of our drift. Less resistance from the rear, a nudge from Norma, a steady pull from Shapley. Why this matter scales beyond cartography. When we calibrate the cosmic distance ladder, bulk flows bias the steps. If you set Hubble's constant using galaxies streaming toward Shapley without correcting their peculiar velocities, you skew the result. Mapping where Shapley sits and how strongly it tugs cleans those biases. It also refines models of structure growth. Simulations under LOSA CDM need to produce Shapley-class concentrations with the right abundance. They do, but the details, feeding filaments, merger histories, are tests you can only run with a precise map. There's a human beat here too. A student staring at a wall-sized plot of streamlines traces the long curve from our local group to Shapley with a dry erase marker. Then steps back and laughs. Not because it's funny, but because the path looks like something you could hike if you had a few billion years. Across the hall, someone sets a small sticker shaped like a kayak near our dot. It stays there through 3 grant cycles. The joke wears into a reminder. We're not just falling. We're being steered by terrain we can now describe. So Shapley is the heavyweight beyond, the range that bends the whole watershed. The Great Attractor guides us toward it. The empty highland behind makes the slide easier, and dark energy stretches the map while all this plays out, which sets up the next tension. If gravity can organize rivers at these scales, how far does that coherence reach before the accelerating expansion thins everything out? The rumor mill called it dark flow. The data has stronger, subtler answers. Dark flow or data mirage? While Shapley loomed ahead and an emptier highland trailed behind, a louder claim hit the field. Maybe the whole observable patch of galaxy clusters was sliding in one grand direction, a motion so vast people called it dark flow. If true, it would hint at influences beyond our cosmic horizon, structures we can't see tugging our entire sky. The stakes were enormous. Either we'd mapped a subtle, local river, or we were feeling a tide from outside the charted ocean. The evidence came from a clever lever, the kinematic Sonyev-Zeldovich effect. Hot gas in galaxy clusters scatters CMB photons. If the cluster has a bulk velocity toward or away from us, the scattering imprints a tiny temperature shift in the CMB at the cluster's position. Doppler fingerprints of motion riding on ancient light. In principle, stack enough clusters and the random noise cancels, leaving a net flow vector. In practice, the signal is tiny and the foregrounds are noisy. A team reported that stacking hundreds of clusters revealed a coherent drift extending to at least 800 million light-years, roughly aligned with the CMB dipole. They called it a dark flow, and for a moment, the room spun. If a flow that large held up, local basins and repellers weren't the whole story. Something beyond our horizon, or a departure from standard cosmology, might be pulling. Then caution kicked in. The method sits on a knife edge. You need exquisite control over cluster profiles, beam systematics, and CMB foregrounds. Misestimate a cluster's gas temperature or mishandle microwave backgrounds, and you can conjure a velocity where none exists. Independent teams reanalyzed the stacks, swapped catalogs, tweaked filtering. Some saw the signal shrink, others saw it vanish within errors. Planck saw sky maps with better frequency coverage to separate galactic dust from the CMB, found no compelling evidence for a coherent suprahorizon bulk flow. The case for a universal drift weakened. Meanwhile, other approaches to large-scale flows, type Ia supernova distances, peculiar velocity reconstructions from galaxy scaling relations, and velocity correlation statistics, painted a quieter picture. Yes, there are bulk flows on scales of a few hundred million light-years. Gravity from structures like Shapley, Perseus, Pisces, and the Sloan Great Wall can do that. But when you push to the very largest scales, the flows damp the way LoveCDM predicts. Large, but not law-breaking. A micro story captures the turn. In a corridor after a conference talk, a postdoc balanced a coffee and said, "I want the dark flow to be real." The senior scientist smiled. "Want isn't enough. Show me a signal that survives Planck." Months later, the same postdoc presented a null result and shrugged. It's beautiful without it. What survived the fire drill? Two things. First, the KSZ technique works. With better data and modeling, it measures cluster peculiar velocities, just not a cosmic tide from beyond scale. Second, the dipole repeller and attractor picture, the push-pull within our volume, fits a wide array of independent probes. You don't need an external hand to explain why the CMB dipole, local galaxy flows, and Laniakea's basin line up broadly. Gravity and emptiness inside the horizon suffice. That doesn't make the episode wasted motion. It refined our instincts. Extraordinary claims, flows that rewrite boundary conditions, demand cross-checks with independent messengers. It also sharpened the idea of coherence. The universe can host extended flows over hundreds of millions of light years without violating the standard model. Those are what you get when adjacent basins share slopes and ranges. But coherence isn't uniformity. Beyond a certain scale, velocities decorrelate, and the Hubble flow dominates. Technically, the dark flow saga improved tools we still use. Better cluster catalogs, multi-frequency foreground cleaning, improved beam calibrations, and stacking techniques all feed into today's KSZ measurements of growth and bias. The null leaned us away from exotic pulls and toward the terrain we can map. The river is wide, not infinite. So was it a data mirage? As a single, horizon-spanning current, yes, so far. As a warning that our instruments and methods can conjure tides from ripples if we're not careful, also yes. Meanwhile, the live story remains richer than either extreme. Our kayak moves under real, measurable influences. Valleys ahead, sparse plateaus behind, woven into a fabric that accelerates. The next question isn't whether a hidden ocean steers us. It's what the accelerating sea does to every river we've mapped. The three endings: heat death, big rip, vacuum doom. We followed the river through basins and past ranges, but the river runs on a planet whose shoreline is moving. Dark energy, the term we use for whatever drives the accelerating expansion, sets the long fuse. Gravity writes local stories. Dark energy edits the ending. Three drafts keep showing. Up when cosmologists push the math forward: heat death, big rip, and vacuum decay. Each is cold comfort. Each answers a different version of the same question. What wins when expansion, quantum fields, and gravity pull in opposite directions? Start with the quiet one: heat death. In this draft, dark energy behaves like a cosmological constant. Its density stays roughly the same as space grows. Galaxies beyond our local gravitationally bound group drift out of reach, their light stretched until it never arrives. Stars burn out. New stars grow scarce as gas thins. Black holes eat the leftovers and over unimaginable spans evaporate by hawking radiation. The night doesn't end in a crash. It thins into a gray, cold fog of low-energy photons and particles. Entropy, the universe's tally of ways to be disordered, maxes out. There's no free energy left to do work. In a heat-death cosmos, the Great Attractor's basin matters for a while. We and our neighbors merge, settle, and keep each other company. Then the horizon closes, the lights dim, and the river becomes memory inside a lonely island. Now the loud one, Big Rip. This needs a twist in dark energy's character. Its pressure must be more negative than a cosmological constant, a case physicists shorthand as W-1. That phantom energy makes expansion not just accelerate, but accelerate faster and faster. Gravity loses territory. First, superclusters unbind. Later, individual galaxies. Later still, solar systems. Far closer to the final seconds, stars, planets, and finally atoms themselves can't hold together. The schedule depends on how far below -1 the equation of state parameter sits. At W just shy of -1, the rip is never. At world noticeably less than -1, timelines people quote are tens of billions of years from now for galaxies to peel apart, then cascades closer together. Millions of years for solar systems, hours for planets, fractions of a second for nuclei. It's a script with an ending you can circle on a calendar if you knew W exactly. We don't. Current observations: supernovae, baryon acoustic oscillations, the CMB, cluster around W equal to -1 with small error bars. That keeps the Big Rip on the table as a theoretical path, but not the favored one. Still, the image lingers, an expansion so insistent it shreds the very bonds that made the river possible. Then there's the trapdoor, Vacuum Decay. Here the villain isn't expansion, it's the idea that our universe's vacuum might be metastable. In quantum field theory, a field can sit in a false vacuum, a local minimum that isn't the absolute lowest energy state. If a quantum tunneling event or rare fluctuation kicks a patch into the true minimum, a bubble forms where the laws inside can differ. Particle masses, forces, the whole rule book. That bubble would expand at near light speed, rewriting physics as it goes. There's no warning, no causal signal outruns the edge. One moment you're in a universe with chemistry, the next you're in one without familiar atoms. It's not an explosion you can survive, it's a clean edit. The saving grace is that calculations tied to the Higgs field, and our best fit parameters suggest either stability or lifetimes. So long they make heat death look impatient. But the possibility sketches a different kind of end. Not running out of fuel, not ripping apart, but a sudden cut to a new scene. Stakes for us sit between these drafts. In heat death, our local island, the remnant of the local group and any friends we catch before acceleration wins, becomes the whole sky. The basins we mapped flatten into solitude. In a Big Rip, even the island dissolves. The Great Attractor's terrain is a chapter, not a climax. In Vacuum Decay, the map doesn't matter, the bubble doesn't care about flows. Meanwhile, the data favors the quiet ending for now. Measurements of W flirt with -1, and every new survey, supernovae standardized better, large-scale structures map deeper, gravitational waves tuned as distance rulers, tightens the leash. The odds shift toward a cosmological constant and a long fade. But a decimal place matters. A small tilt below -1 rewrites the timetable. The uncertainty is honest, not theatrical. There's a human micro-story folded into these endings. A graduate student in a late-night seminar sketches 3 horizon lines on a whiteboard. One closing slowly, one racing outward, one erased by a bubble. They write Laniakea on the first, Shapley on the second, then circle both and add local in the margin. The professor nods. Our river is a local story. The ocean's climate decides the season. That sentence holds the paradox. We can map our slide into a basin. We can feel the push from an empty highland and the pull from a range. And we can still be honest that the larger weather, the equation of state of dark energy, the stability of the vacuum, sets the horizon's pace. So choose your draft. A long, quiet dimming, a catastrophic unbinding, or a clean cut. Each says something about what erasing means. Not deletion, but separation. Not a villain swallowing us, but a boundary moving past what we can touch. The river runs on, even if one day from here it looks like the world ended. Dark energies vote, what the data says. If the river is local, the climate is set by one parameter. Cosmologists call it W, the equation of state of dark energy, defined as pressure divided by energy density. It's a single letter with oversized consequences. If W equals -1, dark energy behaves like a cosmological constant. Steady, uniform, patient. If W dips below -1, phantom territory, expansion accelerates faster, and the big rip creeps from theory toward schedule. If W rises above -1, acceleration can ease. The universe has cast a ballot. Our task is to read the tally. We don't measure W with one instrument. We triangulate. Type Ea supernovae trace the expansion history because their standardized brightness turns distance into a ruler. Plot distance against redshift for thousands of them across cosmic time, and you see whether the scale factor sped up or not. Baryon acoustic oscillations add a second yardstick. Relic ripples in the distribution of galaxies that fix a co-moving length scale. We can spot at different epochs. The cosmic microwave background, frozen when the universe was 380,000 years old, sets the initial conditions and overall curvature. Combine them and you get a constraint on W today, and if you allow it, how W might evolve. When the first supernova teams announced acceleration, the simplest fit was W approcable -1. The best fit dark energy looks very much like a cosmological constant. W within a few percent of -1, with error bars tightening as surveys grow. 2 decades later, with larger supernova samples, better calibration, deeper BAO maps, and CMB data from missions like Planck, providing exquisite priors, the consensus lands almost stubbornly near the same place. That keeps heat death frontrunner and Big Rip a speculative understudy. There's a tease in the decimals. Some joint analyses return central values just below -1, tempting headlines with phantom hints. Others tick slightly above. The shifts are small, and the uncertainties are honest. Systematics matter. Supernova standardization depends on dust, host galaxy correlations, and how you train light curve models. BAO measurements rely on clean selections and robust modeling of nonlinear clustering. CMB inferences intertwine with the Hubble constant, and that quietly contentious number still disagrees between early and late-time methods. Each of these threads tugs on W by a fraction, so cosmologists push for orthogonal checks. Weak gravitational lensing measures the growth of structure, how much the cosmic web has thickened under gravity. If dark energy accelerates expansion, it also suppresses growth. Compare growth histories to expansion histories, and you get a cross-exam. Redshift space distortions, the squashing and stretching of galaxy clustering caused by peculiar velocities, probe the same growth. Standard sirens, distances from gravitational wave events with electromagnetic counterparts, promise a clean ladder rung independent of supernovae. Each of these methods brings W into focus from a different angle. So far, they all point toward the quiet ending. Growth is a little lower than some ZI CDM predictions. Lensing maps sometimes favor slightly weaker clustering, and the Hubble tension keeps theorists awake. But when you project everything into W, the needle sits near -1. That doesn't kill curiosity, it shapes it. The field is pivoted from is there acceleration to is W exactly -1 forever, or almost, or evolving. To test evolution, people write WA as -1 plus a small slope, often parameterized as W plus WA, 1/9 in A, where A is the scale factor. If Y is 0, no evolution. If not, dark energy changes with time. Current data permit a little motion, but not much. The allowed region in the WA plane is a small tilted ellipse brushing -1. Future maps are built to crush it. Euclid in space, the Nancy Grace Roman Space Telescope, Rubin's LSST on the ground. They're tuned for vast supernova samples, precision BAO from galaxies and quasars, and lensing of billions of galaxies. Add next-generation CMB and a steadily growing catalog of standard sirens, and the ellipse should shrink until we learn whether nature likes simple or sly. There's meaning in both outcomes. If W equals -1 to every decimal we can resolve, the cosmological constant survives another trial. and we're left with the profound awkwardness of its tiny value. If W deviates or evolves, the door opens to fields that roll, quintessence, or new physics that mimic negative pressure in more interesting ways. Either way, the climate forecast becomes clearer. A micro story in the midst of this. In a late-night control room, a supernova team watches the last spectra of the season come in from a high redshift candidate. The line fits lock, distance converges. In another building, a BAO team adds their latest. Scale constraints to a joint fit. The software redraws the W contour, shaving a sliver off one side. Someone pins the printout next to last year's. The ellipses overlap like ripples, each smaller than the last. They don't settle the metaphysics. They do something more practical. They decide whether our island coasts into a long dusk or whether a sharper wind blows, and when Dark Energy's vote for now reads steady. The river systems stand, gravity writes local chapters, and the horizon closes slowly. The decimals reserve the right to amend. Life inside a flow, Milky Way's future. Our river has a timetable, and we're on it whether we notice or not. The headline beats are set. In about 4 billion years, the Milky Way and Andromeda close the gap their motions demand. This isn't a head-on crash in the human sense. It's a long ballet under gravity's script. Star clouds pass mostly through star clouds because space is sparse, but the halos, dark matter and gas, interpenetrate, drag, and bind. After a few close passages, the two spirals settle into one remnant, an elliptical, sometimes nicknamed Milkdromeda. If you were alive to watch it on a safe perch, you'd see the sky thicken with tidal streams, new starburst lighting where gas compresses, and then a gradual quieting as the fuel is spent. That merger is the local chapter of a larger drift. The local group Milky Way, Andromeda, Triangulum, and a retinue of dwarfs will tighten into a single bound island. Gravity wins at these scales because the group's internal motions beat the Hubble expansion. Think of it this way. Dark energy stretches the fabric, but nearby knots already tied don't come undone. Our island remains a knot. Beyond that, the flows that define Laniakea keep pulling. If you integrate our motion forward, the merged remnant slides deeper into the basin, defined around Norma, feeling the subtle downhill even as the larger map stretches. Clusters like Virgo drift relative to us. Some we may fall a little closer to, some slide laterally along filaments, but the global edit never stops. The accelerating expansion steadily increases the distance at which bound is even possible. Structures that aren't already married can't meet. The river keeps its channels, the sea pulls the shores apart, stakes sharpen with horizons. In a few tens of billions of years, numbers vary with the exact value of W. Most galaxies outside our local group cross a line in space-time where their light emitted now will never reach us. Not because it's dim, but because the space between us grows faster than photons can close. This is the erasure that matters, not deletion, but permanent separation. The Great Attractor doesn't eat the sky. The sky recedes beyond influence. The map isn't torn, it's redrawn with coastlines we can't cross. Inside the island, life for stars changes on slower clocks. The initial merger triggers a flush of new suns from compressed gas. Then the supply dwindles. Over hundreds of billions of years, long-lived red dwarfs sip their fuel. Planets around them bask in steady, dim light for spans that make all of Earth's history look like an opening act. Meanwhile, black holes at the core lazily grow on stellar snacks, then spend eons evaporating. Gravity nudges residual stars into wider orbits, ejects some, relaxes the rest. The night above any surviving world would be sparse. A local handful of stars, no grand river of Milky Way light, no distant spirals. A quiet sky, not an empty one. There's a practical twist to living in a flow under an accelerating cosmos. Knowledge expires. Today, we can measure Laniakea because other basins still talk to us with photons. In the deep future, an astronomer born on a planet in Milkdromeda would see only the island and might conclude the universe is small, static, and ancient in place rather than time. The clues we use, CMB, afterglow, Hubble flow, galaxies receding, would have faded beyond the horizon. That's the real urgency in mapping now. We're writing the only history some future minds will never be able to reconstruct from scratch. A micro story lands the point. In a lab at midnight, a student overlays our present flow map on a simulation run far into the future. The streamlines in the box of Laniakea stay. The rest blurs and slips away as the code evolves the expansion. They pause on the moment where the local group's remnant sits alone under a small, serene dome of stars. They label it, almost joking, Island Universe. Underneath, they type, what we keep, each other, what we lose, context. So life inside a flow is two truths at once. Locally, gravity keeps us bound, collides our disk with Andromeda's, builds a stable island that lasts incomprehensible ages. Globally, dark energy edits the edges until the island is all the sky contains. The Great Attractor didn't erase us. The accelerating horizon did. And between those poles, our work, maps, catalogs, remembered rivers, becomes the bridge across a future where the current is real but the shoreline is gone. Erasing by expansion, cosmic horizons. Gravity writes rivers, expansion draws coastlines. To see how the map gets erased, you have to learn 3 different horizons: the particle horizon, the Hubble horizon, and the event horizon, each a boundary with a different kind of limit stamped on it. The particle horizon is a look-back ceiling. It marks the farthest light that's had time to reach us since the hot beginning. Every day, that horizon grows because new photons, emitted long ago, finally arrive. It's the edge of our past light cone, not a wall in space, and it grows with time. We're learning more about the early universe because this horizon keeps delivering old news. The Hubble horizon is simpler and slipperier, a scale where the Hubble expansion rate equals the speed of light. 2 dots separated by 1 Hubble distance recede from each other at light speed due to expansion alone. It's not a hard barrier. Light can and does cross that scale if the expansion history cooperates. But it's a useful rule of thumb length that tells you when recession speed first outruns your causal patience. The event horizon is the one that erases. It separates events we can ever be influenced by from those we can never touch, no matter how long we wait. In a universe with accelerating expansion, W near -1, the event horizon is finite. That means there are galaxies today whose present or future light simply never reaches us. They aren't disappearing because they're dim. They're slipping beyond a boundary drawn by the expansion's future behavior. A promise the cosmos makes to itself and keeps. This is what erasing means in practice. Not deletion. Separation. Signals emitted beyond the event horizon cannot arrive. Forces can't cross it. Gravity itself respects the limit. Outside that boundary, mass distributions can't change our fate. Locally, our island remains bound. Globally, the rest of the river becomes uncontactable country on a map we once shared. You can feel the difference between the 3 by what they do to memory. The particle horizon delivers memories, ancient photons you can still catch. The Hubble horizon tells you where recession begins to beat your intuition. The event horizon locks memories away in the other direction. Future light you will never see. As dark energy keeps pace, more of the sky's ledger gets sealed. In the lab of the mind, here's the postcard you can't send. Pick a galaxy just outside the bound of our local group. Today, you could in principle send a radio pulse, a lighthouse beam, a message encoded in neutrinos. In an accelerating universe, there's a redshift beyond which even signals launched now are doomed never to arrive. The space between you grows so quickly, the wave crest gets stretched, slowed, and finally stranded. Your pulse fades into a wavelength too long to carry information before it ever reaches its target. The failure isn't technical, it's geometric. Signals coming toward us tell a parallel story. As more galaxies cross the event horizon, their future light never gets here. The photons they've already sent still stream in for a while, redder and rarer. Their spectral lines stretch, their clocks slow in our view. Then the pipeline dries up. What remains is a fossil sky, nearby companions we keep, distant rivers we remember from archival light. There's an emotional punch hiding in the math. The cosmic erasure is about visibility and influence. History survives in the light already en route. Interaction dies at the horizon. Our gravitational handshake with the wider web weakens because there's less and less to shake. The Great Attractor doesn't stop pulling because it got full. Its pull on us asymptotes to the chunk of it that remains inside our horizon. The rest is beyond reach. It's changing mass distribution a pantomime behind soundproof glass. A micro story brings it close. A researcher calculates the reachability surface for our island, regions of space-time that a future civilization, no matter how clever, could still reach with a probe at near light speed. The surface is a shrinking dome over a thinning catalog. They color the reachable in blue and the erased in gray. The gray eats the plot slowly, then fast. They print it. On the margin, they write, "Not a tragedy, a deadline." This horizon physics reframes the idea of the Great Attractor erasing the universe. It isn't a beast swallowing the sky. It's a foreground actor we can still feel inside a play whose stage is expanding. The erasure is the event horizon's quiet censorship. What dark energy edits out isn't matter, it's contact. What persists are islands, bound structures, floating on a sea whose tides no ship can beat. That lands on meaning. If influence and information are the currency of cosmic society, horizons are the mint. They decide which debts can be paid, which histories can be verified, which friendships can be maintained. Our job now, mapping flows, pinning the basin, measuring W, isn't just academic. It's archiving the part of the river that future eyes won't be able to rediscover. We name the basins not to own them, but to keep them from slipping silently into gray. What's under the hood? Matter, halos, and filaments. If the Great Attractor is terrain, what carved the land? Under the glow sits a scaffold we don't see. Dark matter. It doesn't shine, but it weighs, and on cosmic scales, it dominates. Think of it as the rebar poured first. Gravity pulled it into clumps, halos, that merged into bigger halos. Between them, strands stretched into filaments, and where strands met, nodes formed, clusters. Baryons, the normal matter that makes stars and gas and us, arrived later like concrete poured into the frame. They're the show. Dark matter is the stage. Start small. A halo isn't a hard shell. It's a diffuse, roughly spherical well in the gravitational potential. A galaxy lives deep in one, swirling in the bottom where densities peak. Farther out, the halo blends into the web. A cluster is many halos nested, a city of wells, and the Norma cluster, buried in the zone of avoidance, is one of those cities. When we see the Great Attractor, we're seeing the luminous signs that halos and filaments are stacked there. X-ray hot gas in cluster cores, galaxies marching in redshift along strands, neutral hydrogen whispering from the outskirts. You can tug on the skeleton indirectly. Gravitational lensing bends light from background galaxies, map the distortions, and you trace mass, not brightness. In places where visible galaxies thin, across dust, through fog, lensing still draws the ridge. Weak lensing surveys around Hydra, Centaurus, and into Shapley find excess convergence aligned with the same axes the flow lines follow. Meanwhile, galaxy velocities inside clusters broaden. Thousands of kilometers per second of random motion trapped in the well. Feed those dispersions into the virial theorem and you weigh the halo. The numbers keep repeating. The lights account for a minority of the pull. The web is mostly dark. Filaments are the quiet couriers. They funnel matter toward nodes and set the directions flows prefer. They also feed galaxies. Gas slides along them cold, igniting stars when it hits the dense interior of halos. That's why filaments show up in HI, why their edges sometimes glow in faint ultraviolet, why star formation in cluster outskirts can spike. In the Great Attractor's neighborhood, radio surveys see long, low-contrast chains that bridge from Centaurus toward Norma and onward into the four slopes of Shapley. They aren't pretty on a poster. They're compelling in a model. They connect the dots gravity says should be connected. Baryons complicate the tidy picture. Feedback from supernovae and black holes can heat, stir, or expel gas. That reshapes what we observe without moving much dark matter. X-ray surface brightness depends on gas density squared, so clumping can trick you into over or undercounting. Infrared surveys miss quenched ellipticals. Optical bands drown in dust. That's why multi-messenger maps matter. When X-ray elongations, HI bridges, and lensing peaks all line up, you can trust the contour. In the zone of avoidance, that triangulation is the difference between a ghost and a hill. Why insist the attractor is a region, not a monster? Because halos have edges. A black hole would drink, a cluster accretes. Infall patterns around Norma show caustics. trumpet-shaped lines in redshift versus radius that mark the transition from bound to infalling. That's the signature of a big, finite, well, not an abyss. Surrounding it, splashback marks where newly accreted material reaches a center and turns back, a faint shell that lensing can catch. Those are the fingerprints of a living node in a web, growing by eating along filaments. The pull we feel from hundreds of millions of light years away is the integrated nudge of many such wells stitched together. A micro story from the trenches. In a basement office, two plots sit side by side. On the left, a weak lensing convergence map with a lumpy ridge running southeast. On the right, an HI intensity map with a thin, crooked vein in the same place. A student blinks, flicks between them, then overlays contours. The vein traces the ridge like a capillary on a bone. Across campus, an X-ray specialist emails a temperature map from an obscured cluster. The hot gas halo elongates along the same angle. 3 messengers, 1 filament. It isn't a revelation. It's a confirmation that the scaffold we can't see directly still dictates the route. Simulations seal the logic. Start with initial conditions seeded by early universe fluctuations, evolve under gravity with cold, dark matter and dark energy, and a web appears. Drop test particles where Laniakea sits in the initial grid. Let the code run. The particles stream along filaments into nodes that resemble Centaurus and Norma and keep flowing toward larger concentrations like Shapley. Peculiar velocities in the simulated volume align with basins and ridgelines. The flow maps we draw from data look like the trails in the code drawn by physics alone. Under the hood, then, is a collective pull. Halos within halos, threaded by filaments, punctuated by hot-breathing cluster cores, masked by our own galaxy's smoke. The Great Attractor's gravity is the sum of that architecture. The erasure we spoke about isn't a fanged thing, it's the event horizon slowly severing filaments beyond reach. The scaffold remains where it's bound. The rest becomes outline, terrain remembered by the light that made it over the hill in time. From quantum fluctuations to superclusters, the scaffold we're sliding down didn't begin as a web. It started as whispers, tiny mismatches in density frozen into the youngest light we can see. To understand why a basin like Laniakea exists at all, you have to step back to when the universe was less than a heartbeat old, and then watch the quietest ripples get amplified into rivers and ranges. Inflation is the opening move in that story. In a fraction of a second, space itself ballooned, stretching quantum fluctuations, random jitters in fields pervading the infant cosmos, up to cosmic scales. Think of grain in a piece of wood. Inflation took microscopic grain and ran a planer over it, enlarging the pattern without erasing it. Where the field happened to be a hair denser, the stretching left a slightly deeper dimple in the gravitational potential. Where it was sparser, a slight rise. When the expansion slowed to a gentler pace, those dimples and rises became the seeds gravity could work with. We see their imprint in the cosmic microwave background. Those modeled temperature variations, thousandths of a degree, aren't just pretty noise. They're a power spectrum, a plot of how much structure exists on different scales. Peaks and troughs encode physics, how photons and baryons rang like a drum in the hot plasma, how early gravity tugged, how curved or flat the universe is. Feed that spectrum into simulations, and you get a blueprint. The smallest ripples stall when radiation pressure fights gravity. Larger scales slip past the pressure and start to grow. The pattern of initial bumps sets the menu for everything that follows. Dark matter took the first courses. It doesn't feel light, so it began collapsing into halos before photons decoupled from baryons at 380,000 years. After recombination, when atoms formed and the fog cleared, gas could finally fall into the wells dark matter had already prepared. Filaments stretch between those wells because gravity works fastest along the steepest slopes, and in a randomly seeded field, slopes align into threads. The cosmic web was never sculpted by hand. It was the natural outcome of letting amplified whispers evolve under gravity's simple rule. There's a rhythm to the growth that shows up twice, once in the CMB and again later in the galaxy map. Before recombination, pressure waves rippled outward in the hot plasma around every overdensity. When the universe cooled, those ripples froze in place at a characteristic scale, leaving a preference for that separation, baryon acoustic oscillations. Today, we use BAO as a ruler, but it was born as a ring around a small bump. Stack enough rings and bumps, and you build a field that knows how to grow filaments and nodes with the right spacing. Zoom in on the piece of that field that became our neighborhood. The patch destined for Laniakea wasn't special. It was a region with a slightly higher concentration of bumps on certain scales. Over billions of years, halos merged hierarchically. Small into medium, medium into large, like tributaries becoming a river. Filaments fattened as they fed nodes. By the time clusters like Centaurus and Norma crystallized, the web had already chosen where flows would prefer to go. The basin we call the Great Attractor is a late chapter, not a plot twist. A microstory sits at a workstation. A cosmologist loads a simulation whose initial conditions are drawn directly from a smooth CMB map. They drop tracer particles into the volume where our flow map lives and press run. In the first frames, nothing dramatic happens, just a faint drift toward tiny dimples. Then, slowly, the dimples merge and deepen. Filaments appear as if someone had drawn them with a pencil and then pushed on the paper from below. At 1 billion years, the skeleton looks tentative. At 5 billion, it looks like a map. At 10, you could label Centaurus. At 13, you could draw the basin's contour without guessing. That continuity answers a quiet worry. If the zone of avoidance hides light, does it hide the cause? No. The cause is statistical and everywhere. Inflation spread the seeds evenly. Gravity decided where they would take root. The web's architecture doesn't rely on one hidden monster. It follows from the initial spectrum we've already measured and the rules we test every time we watch a cluster lens background galaxies or weigh itself with hot gas. There's humility in that, and comfort. The river isn't fate, it's probability paid off over time. A little more power on one scale, a little less on another, and a basin like ours forms here, not there. But once the scaffold stands, the details we've tracked, halos, filaments, flow lines, become inevitable furniture. Quantum whispers, inflated to the size of rooms, set the grain in the floorboards we now slide across. The next maps, surveys that will change everything. We've traced rivers we can't see by following how galaxies move. Now we're going to change the light itself. 3 new cartographers, Euclid, the Nancy Grace Roman Space Telescope, and Rubin Observatory's Legacy Survey of Space and Time, are about to turn the fog into contour lines. Euclid is already on station, built to do 2 things at once: measure how matter bends light, and measure how galaxies line up across time. Weak gravitational lensing is Euclid's main lever. Billions of faint galaxies are slightly sheared by intervening mass. Average those shapes, and you get a convergence map of the web, dark matter included. Add spectroscopic redshifts for tens of millions of galaxies, and lensing becomes 3-dimensional. Suddenly, the Great Attractor's basin isn't an inference, it's a tomographic stack. How much mass sits at Norma's depth? How does the ridge towards Shapley grow with distance? Euclid's lensing chips away at those uncertainties, pixel by pixel. Nancy Grace Roman will push deeper into the same space with a different cadence. Its wide-field infrared camera turns the Hubble playbook into a panorama, catching high redshift supernovae and calibrating the distance scale with fewer systematics from dust. Roman also brings bow measured in the near-infrared across cosmic noon, where dark energy's fingerprint deepens. Tie those yardsticks to peculiar velocity reconstructions, and you start decoupling local flows from global expansion with cleaner math. Roman supernovae shave error bars on W. Its BAO anchors the ruler. Its weak lensing cross-checks Euclid's contours. The ellipse around 1 shrinks. On the ground, Rubin's LSST will paint the southern sky every few nights for a decade. It's a movie, not a snapshot. Transients, type Ia supernovae in particular, will be caught early and followed well, swelling the distance ladder with statistics instead of wishful thinking. LSST's photometric redshifts will be shallow compared to spectroscopy, but the sheer numbers, tens of billions of galaxies, make up the difference for clustering and lensing. It's the survey you feed into reconstruction codes when you want streamlines with less noise and filaments traced to their faint ends. The zone of avoidance gets special treatment too. Hi, mapping through dust is booming. Meerkat and Pathfinders to the square kilometer array will pull neutral hydrogen out from behind our galactic plane by the hundreds of thousands. Those 21-centimeter detections supply redshifts where optical catalogs go blind and stitch the filament straight across the mask. Add X-ray missions that pin hot cluster gas even in crowded star fields, and the blind strip collapses into a measurable bridge. The basin's floor stops being guessed. It's measured with independent messengers. Another quiet revolution is coming from standard sirens. Gravitational wave events with electromagnetic counterparts give absolute distances without relying on supernova calibration. One binary neutron star with a host galaxy refines the latter. Dozens will challenge tensions. Fold sirens into the same framework as supernovae and BAO, and the vote on W becomes more robust. If the decimals nudge below -1 were an artifact, this is how you find out. If they're real, this is how you schedule the consequences. All of this helps peculiar velocity science grow up. To reconstruct flows at scale, you need both distances and density. Future catalogs will deliver both deeper and wider. Velocity fields derived from supernova hosts, Tully, Fisher spirals, and surface brightness fluctuations can be cross-validated against lensing-inferred potentials. The Dipole Repeller, the Norma basin, the Shapley range, they'll be delineated in datasets that don't share biases. The push-pull picture either tightens or breaks. Either answer is progress. There's a practical local payoff. Hubble constant estimates that disagree depending on method have haunted cosmology. Better peculiar velocity corrections from richer flow maps reduce one class of bias in local distance measurements. Cleaner BAO and lensing measurements constrain late-time expansion and growth simultaneously. If the numbers still fight after that, we've cornered new physics. If they reconcile, we've retired a long headache. Either way, the map sharpens. A micro story from that near future looks like this. A student logs into a server farm named for rivers, Amazon, Nile, Waikato, and submits a job, overlay Euclid lensing on LSST, clustering across the Hydra Centaurus corridor, with meerkat-high redshifts filling the plane of the Milky Way. The plot returns in blues and golds. The filament that runs to Norma is no longer a suggestion. It's an artery. Across the hall, a Roman analyst adds a new batch of high supernovae to a joint fit. The W ellipse redraws, its long axis shorter by a hair. Someone tapes it beside last year's and writes, "Sharper flows, fewer asterisks." These are the next maps. They don't just make prettier posters. They change what we can say without hedging. Where is the mass? How fast is the coast moving? How long do we have before this river becomes an island no one else can reach? The answers are in the surveys already humming, and the pencil is still on the paper, meaning in a moving universe. When the coastlines move and the rivers thin, meaning sounds like a luxury. But it's exactly what becomes scarce if we don't choose it. The flows we traced, Norma's basin, Shapley's range, the empty highland behind, are facts. The horizons we outlined, what can reach us and what can't, are geometry. What we make of them is the work. Start at human scale. Knowing our island will one day be the whole sky doesn't shrink the value of a sky crowded with friends now. It sharpens it. Maps become time capsules, not trophies. Catalogs turn into letters to future eyes. Every filament we chart is a story we preserve for a night when filaments can't be found from scratch. The act of naming, the Great Attractor, Laniakea, wasn't a claim. It was a pledge to remember. There's another stake, humility without apathy. The basin makes our motion sound inevitable, but inevitability can be a refuge from effort. It shouldn't be. The same physics that says Andromeda will meet us lets us build detectors delicate enough to weigh the basin's floor. The same acceleration that will isolate us gives us a deadline to share. We can't stop horizons from closing. We can decide what we load onto the last ship before the harbor freezes. Meaning also lives in the ordinary. A student pinning another blue ellipse next to last year's isn't just feeding a pipeline. They're sanding down ignorance until what remains fits. A telescope tech swapping a failed cryocooler keeps a survey alive that will teach someone 3 departments away to draw smoother streamlines. A kid with a backyard scope learns the trick with averted vision and stumbles onto the fact that seeing better often means looking slightly aside. That's a cosmology class with the right moral. There's a paradox sitting under all of this. The more precisely we map our place, the smaller we feel. The smaller we feel, the easier it is to shrug. The only antidote is to connect the scales. Gravity turns whispers into rivers. We can turn rivers into archives. The forces that erase contact don't erase care. If anything, they raise its price. Hold one more tension. The river is local, the climate is global. You live in both. That's true of everything that matters. Love is local, justice is global, work is local, meaning is global. The flows are how the universe reminds us the lesson isn't new. So what do you do in a moving universe? You keep your instruments honest. You keep your language clear. You forgive your metaphors when they strain and trade them for better ones when they fail. You build maps that won't be possible later. You teach the next set of hands to read them. You let the scale instruct you, wear the lightness when it calms you, resist it when it excuses you. And when the horizon comes up again, the literal one or the one in a life, you remember that separation isn't deletion. Memory crosses boundaries expansion can't. A final micro-story. In a quiet dome, long after the last tour leaves, an educator dims the lights and brings up a flow field. Arrows sweeping toward a low near Norma, then leaning toward Shapley. They stand alone for a minute, watching the wind of galaxies. Then they turn on the house lights, knowing that most of the kids they'll see tomorrow will arrive late, tired, or scared. They rehearse a line. You live in a river. You're allowed to steer the boat. It won't be the best sentence they ever say. It might be the one somebody remembers. The pull, the map, the end. The invisible hand tugged us into a basin. The map showed the rivers and the range, and the end wrote itself in moving coastlines. If you want the next layer, how these flows set the stage for our far future, watch our deep dive on Horizons. Subscribe if you want more untold cosmic stories. It helps us make the maps while we still can.